mentioned in numerical relativity, the spin magnitude goes from 0 to 1. And in these cases, the spins of the two black holes are either aligned or anti-aligned with the orbital angular momentum. So if the orbital angular momentum is pointing in the up direction, z direction, then for the aligned case, I call it up-up. For the anti-aligned case, I call it down-down. And the figure on the left here shows the orbital trajectory of one of the black holes in each of these simulations. And in the up-up case, because there's more total angular momentum in the system, it requires more time for the gravitational waves to radiate enough angular momentum away so that the black holes can get close enough together and merge. And that's why there are more orbits. And this is called the orbital hang-up effect. And because of this, it also results in more cycles of gravitational waves. So this is the in-spiral part and a zoom-in of the merger waveform. And the simulations I showed on the previous slide, they've also been very useful to calibrate analytical models. Analytical models for defining black hole waveforms. One of these models is called the effective one-body model. And this essentially models, it maps the binary black hole problem to the motion of a test particle that orbits around a deformed curved black hole. And this effective one-body model is useful because it can be calibrated. So there are some unknown parameters in the model, but they can be calibrated to just a few or a handful of numerical relativity simulations. And these simulations have different mass ratios and different spins for the black holes, but then it can be used to predict what the binary black hole waveforms look like for other physical parameters. And the first time this EOB model was extended to black holes with spin was using the simulations that I did previously for the plus minus 0.44 cases of the values of the spin. And this now, this prototype effective one-body model for aligned spins is actually being used as a template bank by LIGO right now. And it was also calibrated to several non-spinning simulations with different mass ratios and some results from black hole perturbation theory that can be used to treat extreme mass ratios. And on this plot, so this is a plot of the waveform from the numerical simulation I did in blue, and also the same waveform that you get from the prototype EOB model. And you should pretty much just see one curve because it just shows that the results basically lie on top of each other. You can get an analytical model to essentially model the numerical relativity simulation results. And it includes not only the in-spiral, but the merger and ring down waveforms as well. So it's unlike post-Newtonian theory where it breaks down at merger. However, the current EOB model we have, it fails for spins above 0.7, which just means that it needs to be calibrated to further simulations with higher spins. And recently, this EOB model was also extended to precessing binaries. What precessing binaries are is that, well, it occurs when you have spins of your black holes that are not aligned with your orbital angular momentum. You're at some degree away from the vertical axis, for instance, and this causes the orientation of the orbital plane to change during the evolution. So I mentioned that there's a need.
Can you go back to the previous slide? This EOB model is also a numerical simulation, or
it's purely analytical. It is not a numerical simulation at all. It's purely analytical.
So it must simplify something for the model.
It basically takes. So there's some unknown parameters in that model that are basically used to match it to numerical relativity results.
Only a few?
That's
I thought your numerical simulation must have many degrees of freedom, and this analytical model have only a few parameters, and somehow it probably can approximate your numerical result, but it would not reproduce your numerical result.
it doesn't reproduce it. I mean, there's always going to be some discrepancy,
No.
but it actually requires surprisingly few simulations to actually calibrate it to match well with numerical relativity results.
Okay.
And that's really what we want, right? Because it's impractical for us to actually use numerical relativity simulations to cover the entire parameter space of binding black holes, because it's just too computationally expensive. And so ultimately we would want to use some analytical model like the EOB model that still makes use of numerical relativity information. But I mean, that's one of the.
I understand you have to check your code, and if you have an analytical solution, you must use analytical solution to check whether your code can reproduce it. But normally, this analytical solution is sort of restricted to certain symmetry. It's a very simple thing that allows you to check.
Right.
And your simulation is to address a much more complicated phenomenon.
Yes.
And that's why I was asking, I mean, what does this model, analytical model, simplify?
So it uses several different pieces of information. It actually does make use of post-Newtonian theory. Post-Newtonian theory has only been calculated to a certain order that's not too high. And so the EOB model is actually rather complicated, but what it does is it uses something called a resummation technique of the post-Newtonian formulas. So post-Newtonian theory is an expansion, but what EOB tries to do is to resum all those terms, to write it in some closed form, to try to capture higher order effects. And that treats the in-spiral part up to maybe the late in-spiral. And it has some unknown parameters, so the merger part really needs the numerical relativity information. But the late ring-down part, it then uses results from black hole perturbation theory to kind of stitch the post-Newtonian and the ring-down together. And there's some stitching procedure that they use for that as well. So I mentioned that to calibrate, for instance, the effective one-body model, to be valid for higher spins, we need numerical relativity simulations that have higher spins. So we want to push the spin limit. And in the past, the highest spins that could actually be achieved in numerical relativity simulations was only about 0.93. And why that is because of how initial data was constructed. And I will also say more about that later. But with my collaborators, we proposed a new method to construct initial data that allows you to achieve spins higher than about 0.99. And why is that important? Well, here's a plot of the spin of a single black hole. And if the value of that spin was 0.93, then that means that you can reach about 60% of the maximum possible rotational energy that a single black hole can have. So if you don't go beyond 0.93, then you're actually missing out on a lot of potential physics. So it's not, it might not be unimportant to go beyond 0.93. So let me then just tell you how we do that. So I said the answer lies in how we construct initial data. And remember that for initial data, all we do is we solve the Einstein constraints on an initial hypersurface. And in practice, we don't actually solve the equations in this form, but we convert it into a form that's more easily adapted to numerical techniques. And We do this by defining a conformal transformation of certain quantities. So for instance, we write the spatial metric in terms of a conformal metric, G tilde, and a conformal factor psi. And we do a similar thing for the extrinsic curvature, where A tilde here involves conformal lapse, defined as psi to the minus 6 times the physical lapse, and U tilde ij, which is the trace-free time derivative of the conformal metric. So these are just details. The main point is that we do some conformal transformation to variables we want to solve for, and then we substitute them back in to the constraint equations, and they then spit out a more convenient form. These are the actual equations. Again, the form isn't the explicit form is not what I want you to worry about. It's just that these are 5 equations that we solve for the shift, the conformal factor, and the conformal lapse. But in these equations, we're free to specify certain things. We're free to specify the conformal metric, its trace-free time derivative, the trace of the extrinsic curvature, and the time derivative of k. And what we choose for these quantities determine the physical properties of the solution we get.
So this is only free for the initial data.
This is only free for the initial data, that's right. So for the evolution, we still need to solve the evolution equations once we have this data. So what is the standard choice then that all numerical relativity groups have used in the past? Well, of course, it's the easiest one. And the easiest one is just to set the conformal metric equal to a flat metric. This choice is called conformal flatness. However, it is known that for a spinning Kerr black hole, you cannot actually write the Kerr metric with this assumption. And if you do, and certainly we can do that in our numerics, but what you get is a black hole that's a distorted Kerr black hole. So if you try to evolve that distorted Kerr black hole, it gives off gravitational radiation. It gives off spurious or unphysical gravitational radiation that we, in numerical relativity, call junk radiation, because it's something we don't want. And it gives this junk radiation off as the black hole relaxes to its equilibrium geometry. And because that junk radiation carries away angular momentum, it turns out that that is what's limiting the black hole spin to be about 0.93. However, though, there's a simple way to get around this restriction, which is to just not use the conformally flat metric. And we propose to use a superposition of Kerr black hole metrics. I hope you can see that in the back, but so in this expression, so this is sum over 2 black holes, and each factor here is weighted by a Gaussian factor around each black hole. So let's just consider black hole 1, for instance. So around black hole 1, this Gaussian factor is about 1. So this is about 1, and these two delta ij's cancel. And in the vicinity of black hole 1, your conformal metric basically reduces to the Kerr metric of a single black hole. And if you're far away from black hole 1, then this Gaussian factor goes close to 0. So you can now you don't have to worry about this term anymore, and your conformal metric still goes to the flat metric. So if we use this choice, then we're able to go to very high spins. And this was done by my collaborators. And this shows the in-spiral merger of 2 binary black holes that have initial spins of 0.97 in the initial data. And this figure here shows the relaxation of the spin due to the emission of that junk radiation. So initially, well, if we look at the inset, initially at time 0, the black hole spin starts close to 0.97, but then the black holes are still not perfect. So the spins will relax. It drops down to this value, but the change now is only in the 4th decimal place, and not 0.93. So this is proven to be quite useful. And at this point, though, no other numerical relativity group has actually used this method. So right now, we're the only group that's capable of getting to such high spins. So I mentioned the problem of junk radiation in our simulations and how it reduces the spins of the black holes. Well, it also messes up the actual gravitational waveforms from our simulation. And so we want to get rid of this junk radiation as much as possible. So this is a picture of a typical waveform from a simulation. And at early times, there's this burst. There's this spike in the waveform, and that is the junk radiation. We want to get rid of that. So to get rid of that, we first have to understand where that junk radiation comes from. And it's essentially because we have an imperfect modeling of the space-time geometry when we solve for our initial data. And there are basically two regions that we need to worry about the geometry in our initial data. So near the black hole horizons, if we don't treat the geometry properly, for instance, if we don't include the correct tidal deformations that each black hole exerts on each other, then in the evolution, the black holes, they will oscillate in their geometry. And this process gives rise to high frequency junk radiation. And if we do not treat the geometry far away from the black holes properly, for instance, if we don't include radiation from the past history of the binary, then this will give rise to lower frequency junk radiation. So these two problems are actually not treated in the method I just talked about for superposing curved black holes for the conformal metric. And more recently, though, I've studied how to include more realistic tidal deformations, so to improve the geometry near the black hole horizons in the initial data, not just by superposing curved black holes, but superposing black hole metrics that have physically realistic tidal deformations in them. So instead of Gij here being a curve metric, Gij here is the metric of a tidally deformed black hole. So this was a recent paper that I did. It's on the archive, and recently was accepted to PRD. But the main result of this work is that if you treat geometry near the black hole horizons more carefully, then you can get a factor of 5 reduction of the high frequency junk radiation over conformally flat, and about a 2.4 improvement over just using superposed curve.
So in principle, if you put the two black holes far enough away from each other,
Yes.
you can solve it even for the tidal distortion of
That's right. That's
the
right.
thing perturbatively.
That's right. Because, yeah, if you treat them far enough, if you put the black holes far enough away, then they're essentially like isolated black holes.
Right.
So these effects, these tidal deformation effects, they diminish, right? Yes. But then that means you, of course, have to evolve them for a long time before they get close enough to merge. So that's the trade-off there. And I said that one of the issues that we wanted to address was to expand the parameter space coverage of our binary black hole simulations. For these simulations to be useful for gravitational wave detection. And we recently computed the most comprehensive catalog to date of binary black hole simulations. And this was a big team effort, so lots of people in the collaboration that contributed. And this catalog contains 174 simulations in total. 150 of them were never presented before. And most of our simulations cover more than 12 orbits. So they typically cover actually a lot more than 12 orbits. And the longest one that we have now is 35 orbits. And that is the current record today of the longest binary black hole simulation. And 91 of these simulations are also for precessing binaries, and the catalog is made publicly available now. So anyone can just log on to this website, blackholes.org/waveforms, and do science with our data. And here's an illustration of that parameter space coverage. So the axis here shows. So the axis here shows spin of chi A is the spin of the bigger black hole. Spin chi B is the spin of the smaller black hole. And the mass ratio, Q, is the ratio of the bigger black hole to the smaller black hole. And each point on this plot represents a numerical relativity simulation. And the arrows on each point represent the spin magnitudes and directions of the two black holes. And most of our simulations fall into 5 categories. In the first category, we have 62 simulations where only one black hole is spinning. Only the bigger black hole is spinning with a spin of 0.5. And the smaller black hole is non-spinning. The mass ratio goes from 1 to 8. So that's along this line here. That's one category of our simulations. We have 32 new simulations with random mass ratios from 1 to 2. And random spins with magnitudes less than 0.5, and that's this clutter of points here. And then we have mass ratio 1 simulations with equal and aligned spins, and including a new one that has the highest spin today. So it's 0.98 now is the current record, and these simulations fall along this diagonal line. And we also included some non-spinning simulations that have various mass ratios. These are just along these lines. These are some easy ones. And then we've also included some simulations with varying eccentricity, from less than 10 to the minus 4 to 0.06. So it's expected that astrophysical binaries have essentially 0 eccentricity, because during their history of inspiraling, they emit gravitational radiation that carries away angular momentum, and the orbit has circularized once the black holes are close to merging already. But there could be a small fraction that has a non-zero eccentricity, and well, the only way to actually know that is to have waveforms that we can actually test against experiments. So this represents the first systematic sampling of slightly eccentric binary black hole waveforms.
Now let me ask a question. When two black holes with different orientation or spin orbiting around each other, do they have a spin orbital coupling, try to sort of align the spin to the orbit?
That's right. They will try to.
So in your simulation, you have this this kind of thing, this kind of phenomena observed?
In most cases, the time scale is too short
Okay, yeah, right.
for that to happen in these simulations. But there's a good astrophysical motivation for expecting perhaps most binaries to have aligned spins.
Yeah.
Okay, and here's just a figure for fun, which just shows all the gravitation waveforms, all 174 of them from our catalog. So that's really it for this slide. And so here's the parameter space coverage of our current catalog. But of course, there are also more simulations in the pipeline. So here's some ongoing runs that I am in charge of doing. So these consist of 95 new simulations to extensively cover the parameter space with aligned spins or anti-aligned spins, or one aligned and one anti-aligned. But to cover that space where the spins could be up to 0.9. So this sampling of parameter space, it nicely complements the current empty regions coverage that we have in our current catalog. And 80%, about 80% of these simulations have completed right now. And these are, again, going to be useful for improving the EOB model and other phenomenological models like the EOB model. So here's some directions for future work. We've made significant progress in covering parameter space, but there's still a large region that needs to be explored. So most of the simulations that we have a mass ratio less than 4, and most simulations have spins less than 0.9. So what remains are certainly more challenging simulations to be done. And we can also try to further reduce that jump radiation that comes in our initial data. And this is a limiting factor in our accuracy for our waveforms, so we would want to get rid of that. But the new simulations that we do have now enable new studies such as analytical waveform modeling, comparison with analytical predictions. That is, we can understand where exactly post-Newtonian theory breaks down. For instance, if we compare their predictions with our simulations, and ultimately then we would like to build waveform templates for gravitational wave detecting. So I've described the problem of binary black holes. Now I'm going to change gear a little bit to show you how numerical relativity can be used to tackle a different kind of problem. Problems that involve concepts in mathematical relativity. And an example of this is for black hole horizons. So I've mentioned black hole horizons several times, but I've never actually said what I meant by that. And traditionally, the surface of the black hole is defined to be the event horizon. So, of course, you know this surface as the region of the spacetime that light cannot escape from. And it is the region of spacetime, it is the boundary of the region of spacetime not covered by the past domain of dependence of future null infinity. Future null infinity is where future pointing light rays end up on. And because of this property, you can actually only locate the event horizon once you know the entire future history of your spacetime. And this is a problem for numerical relativity. And that's because we don't know the future history beforehand. We solve for initial data, so we know what the spacetime looks like at one initial time. And we don't know the entire future history, so we can't locate the event horizon. But we still need to represent the black hole somehow. So
you mean distorted event horizon.
Sorry.
You say you don't know the event horizon, and I take it to be sort of distorted event horizon rather than the symmetric event horizon.
So the actual event horizon, it might be distorted or not. Certainly, like for binary black holes, because they're not isolated, they will be distorted.
Right.
But even that we cannot locate in our initial data.
Right. So I'm saying that with isolated black hole, you know what the event horizon is.
Yes, because you know the future history.
Yeah.
Because it doesn't change, right?
Yeah. Okay.
Yeah.
That's why you need to know that.
Right. Yeah, that's what I mean. But in general, and this will be a general issue, that if you're just given a snapshot of a space-time, that is a space-time at one time, you can't locate the event horizon. So you need to represent the surface of the black hole in some other way. And how we do that is we use something called a marginally outer trapped surface, a concept originating from mathematical relativity. And this is a quasi-local horizon. So it's not, so it doesn't depend on the causal history of your spacetime, but it can be determined just on a single spatial hypersurface. And so this term might be familiar, the apparent horizon. So the outermost marginally outer trapped surface, or MOTS for short, the outermost MOTS is the apparent horizon. And in stationary black holes, that you mentioned before, the event and apparent horizons are the same thing. But not in general spacetimes. So I'm going to go into some more detail about what exactly a MOTS is. So if we consider a two-surface S on a constant time spatial hypersurface sigma,